Okay, guys, session number 3. We're going to talk about introduction of position, course and speed, and related topics to that. So, the definition of a position, course and speed, latitude and longitude, knowledge of the standard navigational terms. We're not going to go too in depth. Then we'll talk about true bearings and courses. We will go into, in a later session, we will go into looking at variation and deviation, but we'll start with true today. And then we'll discuss the knot, basically our speed at sea. So, basics. What are position, course, and speed? What are the basic ideas behind it? So your position, where your vessel is in relation to planet Earth, that's basically what your position is. So if you look at the picture here, that is actually a GPS position on Greenwich Meridian or 0 degrees. So that's crossing Greenwich Meridian, but it's in the southern hemisphere. So it's somewhere in the middle of the Atlantic. Okay, so this information allows you to determine where you are in relation to other fixed objects and other fixed positions. So in other words, if you know where you are, you can relate yourself to where other people are or where other land masses are. If you don't know what your position is, you obviously can't relate yourself distance or in any way safety to other objects. So that's basic principle of position, to be able to relate to where everything is around you. Okay? It's not where your vessel is in relation to other floating objects, unless a fixed position is known. So in other words, it's not, okay, what's my distance away from that vessel? So unless you actually know the position of another vessel, it doesn't really help you knowing your position. So that becomes a relation distance between the two of you, because you're both moving, as opposed to fixed positions, lighthouses, land masses, etc. You can relate to those with your fixed position. Okay? So it means it is not knowing if you are on a collision course. So your position doesn't let you know if you're on a collision course. Okay? It just lets you know where you are in relation to other fixed objects. Whereas we look at course, the direction you are steering, taking into account current, tidal offset, which is known as set and drift. Okay? So any current or tide or wind effect, set and drift, affects your course. So it's where you're going. So that's the difference between a position. A position is just a fixed point. A course is actually where you're going with the various influences on that direction. Whether it's current in an ocean, whether it's tide in tidal waters, whether it's just leeway on what the wind wind's doing to your boat. So getting a course wrong, frankly, you look like a bit of a fool. Okay? Particularly if you end up several miles away from where you planned, from your destination, and now you're down tide, and you spend the next couple of hours explaining to your crew why you're punching into tide as opposed to tucking into a hearty meal at the yacht club, because you've literally overshot your course. So understanding your course, understanding the influences on your course and what's happening to your boat is obviously paramount to good navigation. Okay, now course versus heading. Okay, so course over ground, COG, versus heading. Heading is what your compass course of your vessel is, where the bow of your boat is pointing. It's not affected by anything other than your vessel. So your bow of your boat is pointing in that direction, that is your heading. Okay, so where the bow is pointing, as opposed to course over ground. Now it is shortened to COG, so you will quite often see a GPS saying COG, course over ground. That's what your actual heading of your vessel is, including all the external influences. So for instance, if you're sailing in tide, your course over ground will include the tidal influence. If you're sailing in current, it'll include the current influence. Any windage on your boat, whether it's speeding you up or slowing you down, that will be included if it's pushing you sideways. Now, when we say course over ground, we literally mean ground. So even if you're floating, it's your speed you're traveling over the ground below you, or the course you're traveling over the ground below you. Whereas your heading is literally where you're pointing. So if we look at the little picture here, the green line is the heading. That's where the little boat's pointing. If we threw a bit of current in from the south, we would actually get to that waypoint without actually aiming at it, because the boat will move sideways. Now you see this most particular when people try and cross a river. When you paddle a little dinghy across a river, you actually aim upstream and you go diagonally across, don't you? The same thing with course over ground versus heading. Okay? So that's what your vessel is actually doing. Then your speed. The speed of your vessel, including and excluding set and drift. Okay? So if you look at this picture, you can see my COG, speed over ground, course over ground. 2 I'm circling now with the mouse. Okay? My speed over ground is 1.3 knots. My speed of the boat through the water is 0. So that's purely current or tide. The boat's not actually moving in the water. The boat's moving at exactly the same speed as the water, but we're still doing 1.3 knots over the ground. So that's the difference between speed and speed over ground. Knowing exactly how fast you're going both through the water and over the ground. So a way of thinking about it, you can be standing on a treadmill and your speed is what you're actually sprinting at. So you're running at 2 miles an hour. But your speed over ground is 0 because the ground's moving with you. So that's the difference. So that's the difference between speed and speed over the ground. Now, they're very useful numbers to have both, because you can actually see what's influencing you, whether it's course over ground versus heading, or speed over ground versus your actual speed through the water. So for instance, if you're sailing along, you want to know if you've got tide pushing you, if you've got tide against you, if it's being beneficial or if it's being detrimental to your course, especially if it's going to be pushing you into some sort of hazard. Okay, so where do we derive our position from? Our position is derived from 2 points crossed on a grid system placed around the Earth. So our grids is latitude and longitude. Latitude are the horizontal lines, longitude are the vertical lines. When we refer to latitude and longitude, we always refer to latitude first, then longitude. Don't know why, it's just always been done that way. I'm going to make an assumption here that everybody knows there's 360 degrees in a circle. So if we split, looking at latitude, we split the world down the middle like an egg. And right in the middle, we take our center point, okay, and we wedge it out. So there's our center point. We wedge it out right in the middle at the equator, and we say that's 0 degrees. Then we go 90 degrees up, and we hit the North Pole. And we go 90 degrees down, and we hit the South Pole. And then we wedge it up in degrees. So you can go from 0 at the equator to 90 north or to 90 south. So it's where the lines of latitude lie is where the degree is between the center of the Earth to the crust of the Earth. So that's 15 degrees there between 0 and 15. That's an exact wedge. So it's not just a random grid placed on the Earth. It is actually worked out very, very carefully from where the degrees come out of the center of the Earth. The reason for that is it's completely even around. So if you take the center of a sphere and you work your degrees out and you draw a line on them, it doesn't matter where on the planet you are, if you're at 0 degrees, it is going to be an exact line around the world, and so far up and so far down. So that's why we do it that way. So 90 north or 90 south. Longitude We do exactly the same thing. We egg the world again, except this time we're doing it vertically. Okay, so we take the world and we start at prime meridian and we go 180 degrees one way and 180 degrees the other way. Okay, and then we create vertical lines on those degrees. Okay, so we've got 180 degrees to the west and 180 degrees to the east. That's prime meridian. At 180 degrees either side is your international date line. So that's where our international date line comes from. So if we look at latitude and longitude as a whole, we combine the two together, we've got two grids, one horizontal, one vertical. At this point, I'd like to point something out. Note the horizontal lines are even, whereas the vertical lines, your longitudinal lines, converge as we get closer and closer and closer to the pole. So they're not even. Start with our latitude first, then we put our longitude in afterwards. So we would depict latitude in 2 digits, 3 degrees or 55 degrees, doesn't matter. So 3 would be just above the equator or just below the equator. 55 would be around England or down in the Southern Ocean. Okay. Longitude, because it starts at 0 and goes all the way to 180, we depict it in 3 digits. So it'd be 003 degrees or 147 degrees. They're arbitrary numbers, I just use them. So 3 degrees is either side of the prime meridian, 147 degrees either side, you're almost getting towards the date line. So if we write a latitude and longitude down, you can immediately tell the latitude from the longitude, because the one should be depicted as 2 digits and the other should be depicted as 3. Now, I've noticed on a lot of modern GPSs, if it is 3 degrees, it just says 3. The same on latitude and longitude, which is actually a technical error. It should say 03 or 003. But when we're filling in a logbook, the correct way of doing it is using 2 digits, then 3 digits. Okay, so then we break our degrees down further, and this gives us more and more accuracy. So if we take 1 degree, now I'm using this little scale here. Okay, so if we look at the world, 1 degree, and then we break that down, we break it down into 60 minutes. Okay, so 1 degree is equal to 60 minutes. Now, because you wouldn't look at the world in this respect, those 60 minutes are so fine, you literally wouldn't be able to draw it on a chart like this. So we look at, you wouldn't be able to draw 60 minutes here. It would be thinner than just the line that we're looking at. So we do it in a grid format like this. Okay. So therefore, 6 degrees makes up 36 minutes, 360 minutes. So if we now look at this, we've got our 55, we got that from our earlier. 22 minutes, little dash, would be here. If we looked at that 032 for longitude, and 59 minutes would just be before we go to the next one. So minutes work exactly the same with latitude and longitude. They're both broken up into 60s. Okay, so literally go back one, latitude, 2 digits, 22 minutes is there. Longitude, 3 digits, 59 minutes will be right at the end of the scale. This is where I'm going to go back a few. Remember I mentioned that our degrees, the curve of our degrees gets closer and closer and closer as we get to the poles. Whereas in latitude, our curve is even because it's coming up evenly. This means latitude, this will remain even as you go north and south. Longitude, this will get smaller and smaller and smaller as you get towards the North or the South Pole, which means we can't use it for any sort of distancing. because if we use it for distancing, the same distance, the same amount of minutes in the South Pole would be completely different to the amount of minutes at the equator. Okay, and then we break it down even further. So we break it down into degrees, minutes, and then we want to get even more accurate. So we break it down into a decimal. Okay, so we don't use degrees, minutes, and seconds. We use degrees, minutes, and then a decimal of a minute. And the decimal is of 10 as opposed to 60. So when we depict it, degrees, latitude, 2, 32 degrees, minutes, 0.6, decimal 5. So if we look at this, there's your 32 degrees, okay? There's 6 minutes, there's 5, there's 6, and then half of it again. So when we're looking at how we break minutes down, so when we break one of these little minutes down, yeah, we break them down into 10. We don't use degrees, minutes, and seconds. We just use a decimal of 10. So as your scale gets bigger and bigger and bigger, so these decimals get bigger and bigger and bigger. Okay. Same thing on the longitude sail. We use degrees, minutes, and decimal of a minute. So if you look at where we went back here, we put our little apostrophe on minute there. As soon as we include our decimal, it's a decimal of a minute. It's still a decimal of a minute. It's at the end, because that decimal is a minute of the whole thing. And 1 minute is equal to 1 nautical mile. So 1 nautical mile isn't just a made-up number of where we get it from. 1 nautical mile, because there are 60 minutes in a degree, there are 60 nautical miles in a degree. So the distance of a nautical mile is worked out from degrees broken up into 60 to give us 60 nautical miles per degree. So the distance of a nautical mile is very specific to how the Earth is broken up and wedged in latitude and longitude. Now, this is where we go back to our picture of longitude. If we use a degree as 60 minutes on longitude, it's going to be a different distance to a degree there as we get closer. So we only ever use latitude, because they're even the whole way around the world, to give us that 1 nautical mile. So we would only ever use the latitude scale, the horizontal scale, to give us our distance. The longitudinal scale gets smaller and smaller as you move away from the equator, which would therefore change the distance. Okay, so I'm going to say this here. Marine charts do not, unless they come out of the Dark Ages, use degrees, minutes, and seconds. You can vaguely every now and then find one, but they're very, very outdated. We use degrees, minutes, and decimal of a minute. Okay? And if you want more accuracy, you can go for, instead of decimal of 10, you go for decimal of 100. Go for decimal of 1,000 if you want to do it, but it seems fairly irrelevant. Okay, so I've put this in here. Don't panic, it becomes second nature. It does. Reading latitude and longitude starts becoming absolutely second nature. And I mean, like at first you're going, oh, but all these numbers and this and that. In a couple of practices and you're literally plotting them terribly easily without an issue. Okay. Knowledge of standard navigational terms. Okay, so there's just some standard stuff that we're going to throw in here. We've looked at heading, course over ground, speed, speed over ground, and note speed and speed over ground, speed through the water, speed over ground, position, and lat and long. Those are some major ones. A few others. Charts. Please, guys, charts. All marine maps are called charts. Should never ever use the word map on a boat unless you're referring to the London A to Z, because they're all charts. Okay. Now, if you look at this chart here, this is now nicely exploded. There's land mass, and there's nothing really telling you on land. However, the different colors and contours show you depths. So this has been sort of 3D'd for you if you want for better description. There's a nice view of deep water going into a deep harbor. So that's what a chart does for us. It doesn't give us land information like maps. They are specific to the marine use and only to be used and not to be used for land-based navigation. And the same thing is, you don't use land-based maps for nautical navigation, ever. Never, ever, ever do it, because you don't know what's underneath the water. This brown bit, this bit, the whole lot might be flooded. So all you can see there is just one big flat piece of water. But you might go along here and hit the bottom. That's like 0.6 of a meter there. And if you've got a 2-meter boat, you're going to hit the bottom. So without a chart telling you where this channel is, you won't know where to go in. Inversely, that's if you have a map, it doesn't have that information, you can't get there. Inversely, if you're trying to navigate from there to there on land, well, there's no, you see the road's just sort of half detailed. You can see it just peters out. Details of the land are very poor. Okay, so they contain information specific to the marine environment, hence the word charts versus maps. Okay, one thing to make sure of, don't assume colors and symbols are the same on each chart. They are not. So if we look at this chart, land is green, shallow water is brownish, whatever, sandy color, white getting darker blue. That's just this chart. Look at the next chart, land is brown. So the colors aren't the same. Here's land that's green, there's land that's brown. Green is the shallows. Dark blue is the slightly shallow water. We go back here, white is the shallow water, dark blue is the deeper water. So don't assume the colors are the same. Okay, compass rose. Every chart needs a compass rose. What we've got here, there's our true north, and we've got our magnetic variation detailed next to it, inside it. Okay, and we'll go into much more detail on that. But that is pointing to the top of the chart, true north. So if we remember our longitudinal scale that worked its way all the way to the top of the planet or all the way to the bottom of the planet, our longitudinal scale, the vertical ones, will always point straight up to the top of your chart to true north. The latitudinal scale, the horizontal ones, which were evenly spaced, will always be 90 degrees to your chart. So those will always be true north, will always be straight at the top. That will always be 90 degrees to it. Magnetic, we then need to work out later. Okay, so magnetic. Many charts might well have more than one magnetic rose, because there might be more than one magnetic influence on a certain area. Large scale charts might have lots. A true north at the top, pointing the top of the chart. So true bearings and courses. So taking into account that everything at the top of the chart is true north, true bearings and courses is what we use on charts. So it doesn't matter what you record with a magnetic compass or GPS or anything else, whatever you draw on your chart must be true. Okay, so we always draw true bearings, true courses on the chart. So if our current happens to be coming in this direction, we will draw it as true. So in this case, we've got a current going like that. So it's pushing the boat this way, down to this corner. So we've actually got a heading up there to go on that line. Lots of current pushing the boat that way. We've got to counteract it to go straight across. So that's your heading. That's your course over ground. Okay, so this is exactly what we have to plan to do. We want to go from there to there. How do we do it? What heading are we taking to get from A to B to C to D? So this is navigation. Okay, so red is the true course. That's actually what we did. Yellow is the direction of the wind or current, tide, any water movement or affecting us. And then green is our heading. So I've just used those colors just to detail it correctly. You put them all on a chart with a pencil anyway, so the same charcoal brown color anyway. But you can actually see, and I'm using from C to D, if you've got quite a strong current going that way, if you want to go from C to D, you've got to point the boat there. So as you're pointing it there, you're going to follow up this line. And I've pointed it like that because you see how my mouse is pointing? That's how my boat will sail. My mouse is pointing the same as my heading. That's how my boat will sail. His heading will be like that, but he'll actually be crabbing sideways as he goes across there, because the current will be pushing him down. So he's having to counter with the current by changing his heading. And then you can work out all the distances and all that sort of thing, which we'll look at. So keeping accurate records is essential for good nav. You need to know what the current's doing to you. You need to know what the wind's doing to you. Therefore, you can navigate and plan correctly. Okay, and we'll go deeper into that later in the courses. The knot. Where does it come from? The word the knot actually comes from these sort of galleon type ships. They had a specific size board and a roll with a line, and each section of the line had little knots tied on it. Full knot, half knot, 2 knots, half knot, 3 knots, half knot, 4 knots, and so on and so forth. That had a small drag on it, and they would drop this board over the back, and they would let it drag for a certain time, and then depending on how many knots came out, that was their boat speed. Not very accurate, but that's where it came from. Nowadays, it's far more accurate. Okay, so we drop the line out the back, drag it, count how many knots, and that will be our boat speed. That's where the word comes from, basically, nowadays. We never use any of that. Okay, all that's left is the word knot. Okay, the knot today is the name given to 1 nautical mile per hour. Okay, so 1 nautical mile. Remember, a nautical mile is 1 minute of latitude. So a knot is how long it takes you to do 1 minute of latitude in time. 1 nautical mile per hour. So if it takes you 1 hour to do 1 minute of latitude, which is then 1 nautical mile, it is a boat speed of 1 knot. So therefore, if you do 6 nautical miles in an hour, you are doing 6 knots. If you do 5 nautical miles an hour, you're doing 5 knots. Okay? A knot is speed it takes to cover a nautical mile. So a nautical mile an hour equals a knot. And we still refer to it as a knot. We don't talk about nautical miles an hour on board. It's a bit of a mouthful, nautical miles an hour. How many knots are you doing? Don't get the nautical mile an hour confused in any way with a statute mile. They're different distances. So the miles that we see on the motorway, it's 40 miles to Eastleigh. They're different distances to nautical miles. They're not the same. Statute miles are different. Okay. So we spoke about this. Never ever use the longitude to derive your miles per hour, because they converge. So that distance, which is 15 degrees there at the equator, there's almost no gap when you get up north. So you can't use longitude at all. So always use latitude to derive a nautical mile. So always use the latitude scale. It's It's always on the sides of your chart, never the bottom and the top, because that's your vertical scale, your horizontal scale. These will be even all over the world. These will converge as they get closer to the poles. Okay, so if you're doing a nautical mile in an hour, you're doing 1 knot. If it takes 30 minutes, we're doing 2, and so on and so forth. If you're doing 10 knots, it'll take you 6 minutes to cover a mile. So it's just a normal time speed calculation. Very, very simple. So if you take 10%, then you're doing whatever speed. You can just say, if I'm doing 6 knots, then I have covered 6 nautical miles if it took me 60 minutes. So a nautical mile in meters is 1,852 meters. And for those of you who are ever planning on doing a qualification, that's an absolutely favorite exam question. How long is a nautical mile? It's 1,852 meters. If we take a nautical mile and we divide it by 10, remember our degrees, minutes, and a decimal of a degree is what we have for our lat and long. So we take our nautical mile and we divide it by 10. That's called a cable. The 10 cables to a nautical mile. So it's 18.52 meters. So if that's 1 nautical mile, 1/10 of it is 1 cable. So that's what a cable is. So if you hear somebody saying, oh, can we pass you 3 cables to starboard? That means they want to take a third, 0.3 of a nautical mile away from you. So instead of talking about 0.3 of a mile, 0.5 of a mile, we just talk about 1 or 5 cables. Cable is 1/10 of a mile. So there's 10 cables to a mile. See there? 1 little cable there. That's him. Okay. We're just about run out of time. It's just scratching the surface, but it gives you an idea of where lat and long comes from. It's not just a grid that's randomly thrown on the planet. It comes from the center of the planet in degrees, nautical miles, and distances, and marine distances, again, are not just random distances. They worked out from those degrees by minutes, 60 minutes making up a degree, but it gives you a good idea of what we look at. And then our knot, which is then made up of a nautical mile per hour. So the whole lot sort of intermingles quite nicely. When you do go into theory courses, they go quite heavily into this, quite heavily into the navigation. Okay, and don't get flustered about it. It'll start making perfect sense once you start using it. Once you actually start plotting positions and trying to do bits and pieces, it makes absolutely perfect sense. For those of you who've got a little bit of interest in it, the app that I use when I'm navigating on my phone, just as a backup, is Navionics. Pretty simple app, but it works very well. And you just pay for the charts of the area you're working in. So, normal. You pay for your charts if they're paper, you pay for your charts if they're electronic. Normal. So, same thing. You've got those numbers already. Next week, we'll go through a bit more detail of charts and the publications attached to them, information shown on the charts, chart symbols, representation of direction and distance, navigational publications in common use, and chart correction. So basically, some of these books you're looking at here.